We're now ready to take a look at three-dimensional vectors. Okay, so everything in the past we've done is 2D. We're going to take a look at what they are as far as like geometrically, they're pretty much very similar, obviously, directed line segments. Okay, but we're really going to be looking at trying to organize our brain to think properly, to be able to understand vectors in three space and what it means. All right, we'll look at the algebraic vectors and we'll take a look at how to calculate the magnitude of a vector and how we change our concept of direction, okay, for three-dimensional or 3D vectors. Okay, how we're going to take a look at this. First of all, we are going to do this investigation, or I want you to do it. But first, I want you to take a look just simply, okay, at our old two-dimensional grid system, right? This was the y-axis, vertical, and horizontal was the x, okay? Well, in 3 dimensions, we have to add a third major axis. And what we do is we kind of fool our brain. We go basically at like a 45, draw a dashed line to represent the third axis. Imagine in our brain that this is coming out of the page, okay? So everything on this side is coming directly out of the page at you, and everything on this side is under the page, okay? So it's behind, I guess, the vertical and horizontal axes, all right? We also change where the axes are. So the horizontal is no longer the x, it is in fact the y. So we have the y-axis on the horizontal. The z-axis is now the vertical, and the axis that's coming in and out of us is the x-axis. All right, so you got to think of it that way, okay? So we're trying to change our mentality. We're trying to see things a little bit different. And yeah, we're drawing on a two-dimensional plane, and we're trying to imagine our brain having this image three-dimensional. All right. What we're going to do with the investigation, okay, that I want you to go through is basically imagine what any point out in space is going to be. First of all, we have this triplet. So it's the X, Y, and Z coordinates, right, for the point. How does that relate with a position vector? Again, starting at the origin, you can see the origin is now 0, 0, 0. All right. And what would this position vector be as a vector? All right. I'll tell you right now, it's very simply if we add the square brackets. Oops, sorry. I was doing the zero vector again here, but OP, vector OP is just with square brackets, X, Y, Z. Okay, now this is the idea. Now, to help you with this idea, all right, I want you, again, pause the video, all right, and go through this investigation. All right, if you take a look, this classroom is set up the same way as the grid system is. All right, you can see we've got the X coming out at us, we've got the Z vertical, and the Y is the horizontal. All right, they happen to have different side lengths, right? The left wall is 10 meters long. You can see the cubes all there, or the squares. The front wall is 8 meters, and the wide, or the floor is that wide, right? And the front wall is 4 meters high. Okay, so pause this and go through these questions on your own. All right, understand each one. Try your best to go through. Okay, and then after you're done with these and you're thinking about it, it should take you, I don't know, maybe 20, 25 minutes or so just to look through it. Some of you may go a little longer or a little shorter. Okay, but go through, think of it on your own, some of the questions there. All right, and then restart the video. All right, and we'll summarize some of the things. And if your questions aren't answered, then you can ask them either in our Teams meeting or an email through me. Okay, so you can pause the video now. So now that you've gone through this, hopefully you went through, you could take a look at a couple of the things, right? All right, that you should know by now. We've got new terminology, right? We have an octant, okay? The octants is because now our space is separated into 8 different spaces, right? Quadrants, because there was 4 of them in 2D. In 3D, we have 8 of them, right? And they each have different, the points are different. You know, the first quadrant is positive, positive, positives, right? You have those where everything is on the top and the basically to the right hand side. All right. If we are doing above the z-axis again, we could have, there's 4 of them above the z-axis. You can have a negative, positive, and a positive, right? And then a variety with the positive, negative y values as well, right? So all the way around the 4. So you've got those. We're going to take a look at you know, the major planes instead of a major axes. You notice that we have 3 major planes, okay, that cut basically right through the middle of this of these octants, right? The XY, the XZ, and the YZ plane. Okay, so let's just take a quick peek. I'll go back to this diagram in here. I'll get rid of my p-value, we don't need it. But if you take a look at the planes themselves, right, I'm going to go in with a different color. Just I'll use the blue here. The XY plane that we've been using, you know, all along up until this point is basically, you know, this one over here. It's listed and it's the horizontal plane. All right, so we can see that. So you take a look, the XY plane, right? Okay. Let's take a look at the ZY. The ZY you should be able to see pretty clearly. The ZY plane is this vertical plane, right? Cut straight across, flat across your paper, all right? And now the XZ plane, right? We come up, we go out, we go down, and I believe we go down there too, and there you go. Cuts through, right? It's kind of vertical with us. If we were to position this, all right, our perspective would be right on the edge. Okay, it would almost look like it's the z-axis, you know, if it was positioned correctly, if we could spin this around. Okay, so those are your 3 major planes, right? Let's take a look at how do we come up with what a vector actually is. Geometrically, right, all vectors have a magnitude and they have a direction. We can see the direction if we have the directed line segment on the grid itself. But algebraically, what is the direction? Algebraically, what is the magnitude? So what we're going to do is I'm going to take you through, this is already worked out, okay, the magnitude of the Cartesian vectors, same as algebraic vectors, all right, means the same thing. All right, and I'll go through kind of line by line, but I want you to take a look at the diagram you can or that you can see here. So we're looking at what is the vector v in this case, and v is the vector OP. All right, O is the origin, P is the XYZ, okay, at the head of XYZ there, the point there. All right, and let's take a look how we find out what the magnitude actually is. Okay, so all the setup is already there. If you take a look at the points, A is on the x-axis. So it is basically an x, 0, 0. B is on the y-axis. So it is the point 0, y, 0, right? C, again, being on the z-axis, is 0, 0, z, okay? If we look at ON, and it's set up basically as the projection of OP right onto the plane, the XY plane, we can see that N itself is going to be X, Y, 0. All right. Now, we're looking at things that are basically all 90 degrees here, okay? Orthogonal, all right, to each other, or normal to each other. If we want to find out the magnitude of the vector, which we do, all right, we can see that we've got a right angle triangle, okay, between O, C, and P. And so looking at V as the hypotenuse, the magnitude is the hypotenuse, we can say that it's OC squared plus CP squared. Okay, so OC squared plus CP squared, right? Take a look at CP. CP itself is identical to ON, right? If you take a look at that rectangle that's formed, OCPN, that's a rectangle. All right, CP is equal length to ON. So we just transform the CP to ON, and that's what we have in the second line. All right. Now, what is ON? ON is the hypotenuse for the triangle OBN, right? This is perpendicular, so it's the hypotenuse, the ON. So that means we use Pythagorean theorem again, and we get OB squared plus BN squared, the magnitudes. Okay? Now, the last thing, BN is identical to OA. It's the same length, the rectangle down on the XY plane. And so we substitute the OA, all right, squared inside there. And we know that the magnitude of OC is Z, the magnitude of OB is Y, and the magnitude of OA is X, because that's just the length. So when you take the square root, all right, notice that OP, we just substituted that in for vector V, okay? When you take the square root, you basically have the same formula that we did in 2 dimensions, except we just add that third coordinate or component in there, okay? So that's the magnitude of a vector in 3D. Nothing earth-shattering, but just the process of how we find it, okay? All vectors have a direction, so now we take a look at how we figure out the direction, okay? Again, it's already set up here for us, all right? But what we do is we're going to look at direction angles, all right? And from the direction angles, we find our direction cosines as well, or vice versa, all right? So the way that we look at the direction in 3D, we don't just have one number, okay? We don't just say, okay, we're just going from the x-axis and the x-axis and find out what the direction angle is. We have 3 direction angles. And what they are the angles from the positive axes, the x, y, and z, to the angle or to the vector itself, okay? So if you take a look at, okay, these diagrams, this final diagram, all right, that you should have already looked at anyway, okay? Alpha is the direction angle for the x value. Beta is the direction angle for the y value. And gamma is the direction angle for the z, okay, value. So here's how we find this out. Taking a look at this diagram, I think it shows it really well. We're going to look at a triangle here. If we start at the origin O and work our way across the x-axis to A, then we take the diagonal from A up to P. And then we use OP to complete the triangle. Okay, that's the triangle that we're looking at. Now, alpha is this angle. Excuse me. Okay, that's clear. We can see that. But what's not as clear is we have to imagine this in our heads here is what is this angle right here? Okay, so I'm drawing it that way on purpose because that angle is in fact a 90-degree angle. How is that a 90-degree angle? Well, the outside back wall here, okay, if you take a look at this back wall is perpendicular to the left wall. Think about that. It's perpendicular. That means it's at 90 degrees to the left wall, which means that the angle in question, okay, or sorry, let's say A to P is on that back wall. And so that line joining A to P is perpendicular to any line on the left wall. In fact, the OA line, okay? That's going to be true if we wanted the beta or the gamma, right? From the Y value or the X value. But understand that we're dealing with right angles. And since we're dealing with right angles, we know that from theta, this is the adjacent side length, right? That's the adjacent side length. This is the OP is opposite, and AP is the hypotenuse, all right? Because the right angle, or no, sorry, I did that wrong. And I can see why I did that wrong. But if we take a look at it, because this is the right angle, this is the hypotenuse. The OP is the hypotenuse, right? And the AP is the opposite. All right, now that's correct. So from there, if we look at the cos of alpha, the cos of alpha we know is the adjacent over hypotenuse. The adjacent is OA, right? The magnitude of OA, which is just simply x, divided by the hypotenuse, which is the magnitude of OP, the vector we want. So basically, the cos theta, or cos alpha, is x over the magnitude of the vector in question. All right. Similarly, if we're looking at beta, cos beta is y over the magnitude of OP. And finally, cos gamma is z over the magnitude of OP. Okay, the direction cosines, all we do is use cos inverse for the direction angles. Okay, direction angles must be stated in order, alpha, beta, gamma. If they're out of order, we change the direction of the vector, and we don't want that. We want to keep it set. Okay, so hopefully that makes some sense. Okay, there is an example that we have in here. So here's where we have what our direction angles are. Okay, a very quick proof you can see here, and I know you're going to use something like this in some of the homework questions there, is just proving that the sum of the squares of all the direction angles is equal to 1. All right, and the solution is very simple and straightforward. When you take a look at what the direction angles are and then square them, right, you're just getting x squared plus y squared plus z squared, which is in fact, right, it's basically the magnitude of the vector itself. Okay, squared because there's no square root sign. And then the bottom we have everything squared, so it's the magnitude of the vector itself squared. So you get basically 1. Okay, so you take a look at that. An example, we've got any old vector, find its magnitude and its direction angles. Okay, so just by looking at this one, we'll do another one so we can see it. Okay, but by looking at just straightforward magnitude, by looking at the definition of what the direction angles are, okay, you can come up with 3 specific angles from the positive coordinate or axes, x, y, and z axes, and that'll give you this precise position of the vector itself. Okay, so let's just do a simple one, and we'll just call this example 1, and we'll have our vector being 2, -4, and 5. Okay, it really doesn't matter. So to find the magnitude, we know, first of all, that we're looking at the square root of the sum of the squares. Okay, so 2 squared plus negative 4 squared plus 5 squared, right? 4 plus 16 plus 25, the square root of all that, and you've got the square root of 45. All right. For those of you who like to simplify this a little bit, you're going to end up with 3 root 5 because it's 9 times 5, square root of 9 is 3. Okay, so you've got that. Anyhow, looking at the direction angles, you take each one individually, right? So you're looking at alpha is the cosinverse of 2 over the square root of 45. Okay, so put that in your calculator, right? Cosinverse 2 divided by square root of 45, and you get approximately 72.7 degrees, right? Beta, cosinverse, you use the y value, it's a negative 4, which means that it's probably going to end up as an obtuse angle. So cosinverse minus 4 divided by the square root of 45, and there we have approximately 126.6 degrees. And finally, gamma, we do with cosinverse of 5 over the square root of 45, and we say cosinverse 5 divided by the square root of 45, and we have approximately 41.8 degrees. Okay, so we have vector A has a magnitude of square root of 45 degrees with direction angles 72.7, 126.6, and 41.8. Okay. All right. The other things that the last couple of examples here, just showing things that you should be able to do, and I'll just talk through this example here, because if you're not given the vector at the origin, you find the position vector, right? And I think it makes sense to do it that way. Understand geometrically why we're doing things this way algebraically, okay? If you've got your vector A, or your point A, your point B, okay? That's a B in there. Find AB, right? The magnitude of AB in here. Well, we have to come up with, well, what is the vector itself? All right. Understand that if we take from the origin, the vector OA, and then the vector OB, this is set up because OA and OB are set up tail to tail. We're set up as a subtraction. And remember, it goes from the head of the second to the head of the first, right? The head of the second to the head of the first. So it starts at A here and goes to B. That means that that point A, that's the second one there, right? So from the head of the second to the head of to the first there, right? So we end up with OB minus OA. All right, and that's what AB is, the head of the second to the head of the first. All right. So you can see how the math works out. In this case, getting the vector 6, negative 7, negative 1, using the magnitude formula that we have, we can come up with the 2 root 26. Okay. Finally, with this one, show that triangle ABC with those vertices is equilateral. Equilateral means that the side lengths are all equal to each other. If the side lengths are all equal to each other, then the vectors that form those side lengths have equal magnitude. That's the idea. So basically what you're looking at is you want the magnitude of vector AB, vector BC, vector AC. Show that they're all the same and equilateral. As a thought, What if it's a right angle? What if it says to prove that you have a right angle triangle? What would you use to prove it? What could you show? Right angle triangle. A right angle itself means that the dot product between the two vectors, the sides, right? The dot product is equal to 0. So if that were the case, and I don't believe it is in this case, but if it were the case, that's how you would show that something is perpendicular or not perpendicular, right? If it's not 0, it's not 90 degrees. All right, so that's just the idea there. Try a hand at these questions here. Good luck and let me know if you have any questions.